This week on The Futurists, Roberto Siagri. Welcome back to The Futurists. I am your host, Brett King, back in the hosting chair. And this week it's my turn to say that Robert's not available, but we have an excellent host sitting in the chair with me, returning part of the Futurist family, David Orban. Welcome to the hosting chair on The Futurists.
Thank you. It's an honor. And I know I have big shoes to fill, big chairs to fill, as it were, because I listened to the show with Robert and you hosting, and it is excellent, very entertaining, and very, very enlightening.
Well, it's great to have you back with us. And maybe you could introduce our guest for today and tell us how you guys know each other as well.
Well, for me, it is a real pleasure to have Roberto as a guest. We've known each other for many years, almost 20 years now, and I've known him to be always in the forefront of innovation, not only from a theoretical point of view, but implementing new ideas in electronics, hardware, high performance computing, and now in quantum computing, so that enterprises and people all over the world can benefit from innovation that maybe we just have been reading about before. And when I've learned that his new project, new startup, Rotonium, closed a round of funding in its ambitious plans to bring quantum technologies literally in the space age, I thought he would be a perfect guest for the Futurists podcast.
Roberto Siagri, welcome to the Futurists.
Thank you. Thank you for having me here with you.
And where are you coming to us from?
Well, I'm based in Italy, and I am a physicist as a in some way student, but then I try to practice in the industrial sector the theory and how we can get physics to a point that can be useful for all humankind.
So we've had theoretical physicists on the show, but you're a practical physicist.
Besides that was a theoretical physics in the beginning, I tried to figure out how to implement it.
Very good. Very cool. And I definitely want to get into quantum, and Rotonium, your new startup. But let's start with when did you know you wanted to be a physicist and building the future?
Well, but just from the early days when I was a kid, figuring out that science was the only way to understand the world and to have a much clear view of what is the world. And in reality, the aspiration was to understand the universe, why we are here, which is our purpose in the universe. So I started from astrophysics, and then I moved to solid state physics, and the combination of the two, now I've put me in this new nice spot of quantum computation that is in reality something that challenge ourselves to understand what is reality and how we can understand in a better way reality.
Is reality even real? Yeah,
exactly. Great question. Exactly.
This is the question physicists are always asking, right? Have we created our own reality? It's mind bending, isn't it?
I can tell you that in this investigation that we are doing inside photonics, we are figuring out that we do not have really understood what is space and time, and maybe space and time as we know them are not exactly what they are.
Yeah.
So it's what it is really is a great question.
Even now, yeah, absolutely. Even string theory is being challenged at the moment, and so forth. It's each step we take further, we know how much we don't really know. It's an exciting
Absolutely.
time in history.
Absolutely.
All
And
right, cool.
if I
David,
may, to
please.
add, I am not a physicist as Roberto, in the sense that I do not have a physics degree, but I'm a physicist at heart because I studied physics and I love physics, and I am so lucky not to have pursued a career in physics, because now 2 generations of physicists practically wasted their lives pursuing as you mentioned, the string theory, which we haven't even proven wrong.
Yeah.
It is such a mess. We have not found experimental evidence for it, but even the theories are a mess. And I think from an epistemological point of view, it will be extremely useful to go back and see, could we have done better? Are there lessons we can learn on how to do science differently so that we don't squander such an outrageous talent as it has been the case in physics for the past 50 years? And luckily for Roberto, quantum technologies are exotic, yes, but extremely well understood. When people say, "Oh, uncertainties and entanglement, quantum this, quantum that," a lot of hand waving, they actually don't realize that our most precise theoretical predictions matching experimental evidence at the longest number of digits, a precision that nowhere else we can find in science or engineering, is in quantum electrodynamics. And that kind of prediction is a proof of the power of the theory and a wonderful premise for its applicability. So starting
Yeah.
from that, I would like to ask Roberto how and why he thought that his next endeavor would be using quantum technologies.
Yeah, and let me just before to answer the question, add one thing to your what you have said. Sometime or nowadays we know how to compute things. Maybe we do not have understood exactly why that kind of things happen, but that David is right. We know how to make the calculation. We know how to do these things. The hidden layer, maybe it is not very well understood, but it's good. What we know is good enough to build up stuff. And what we are doing, for instance, we are doing these photonic quantum computers. We are trying to build up. We have designed a new type of qubit that is using photons. And why I started these things? I think that you remember the Superman movie in the Fortress of Solitude maybe in the North Pole, in which Superman make computation with crystal. Have
That
this
was a
crystal.
quantum computer? You're telling me that was
No,
a
I do
quantum
not know.
computer?
I do not know. It may be possible because I do not know how you can do that if it is not a quantum computer.
Yeah, I get it. I get it.
So it's just with crystal, just with light, without any other device, it was able to compute. So that's smart, that's very efficient and not very big and all that. So that's was puzzling me, how we can do computation with light. And so that's 20 years ago idea, but then I have wait the technology and the production, all the capability to manufacture at the small scale devices in order to implement then this theory. So, and I think that now we are in a really nice spot in terms of a convergence of the semiconductor manufacturing processes, understanding of how light works and the quantum theory, and also the algorithm. We start to have quantum algorithm. So it is a combination of many factors that have bring me in this field.
So can I drill down on that a little bit first, David, before we jump into that? I mean, quantum computers are often referred to as probabilistic computing machines versus the way we think about classical computing. Is that an accurate way to think about the way algorithms resolve results in quantum computers, or is there a nuance to that?
Well, it's a little bit tricky to say that. It's quantum mechanics is deterministic. The point of the probability is coming because we try to interact with the classical world with the quantum world. So when we extract from the quantum world the data or the information, then we have to that this kind of probabilistic things happen. But in reality, quantum mechanics is not probabilistic. And what David have said about the numbers, so if you're able to compute as 20, 30 numbers after the comma, it means that that is not probabilistic.
Okay.
But in the way in which we understand it, in the way in which we look at it, it looks to us as probabilistic. But when we compute, you can compute in a deterministic way, and you can also compute in a probabilistic way, both, of course. But in the essence, it's not probabilistic.
Thank you for that.
And Brett, if I may add, we have had quantum technologies in use in our daily lives for a long time. Our semiconductors work because the electrons are able to overcome barriers that would have been completely impossible were it not for quantum effects. Or our GPS works because we are using atomic clocks that are synchronizing the satellites with the ground stations, and as a consequence are able to calculate our position at 3 feet or even at a lower, at a higher, finer resolution. So in the past almost 100 years since we discovered the quantum nature of reality, there have been important steps we've made, not only from a theoretical and an experimental point of view, but also starting to implement them. And now with quantum computers, what is happening is that we are starting to take advantage of these phenomena rather than recognizing them as a necessary component of nature, but being a bit queasy about how they work. And I think it is useful for Roberto to tell us a little bit more how qubits, that are the equivalent of bits in quantum computers, storing information that gets manipulated, in his case, for his particular architecture, which is based on photonics, quanta of light, representing the units of information rather than electrons, right? Like in our normal computers. Why did you decide this would be your approach, Roberto? And why do you believe is superior or has more promise than other approaches?
Well, first of all, I have said before, the idea was to follow this crystal approach in the fortress of solitude of Superman, but in reality is based on physics. If you want to design something that can operate at room temperature,
right,
it is difficult to envision this with superconducting qubit or with atom or neutral atom qubit. And there are also other technologies like ion, but they need a very complicated equipment in order to keep them in the right position and to cool down them with laser. So the problem is complexity. The idea is that photons are quantum at room temperature. Light is quantum. So the point is how you can select from billion of photons that are coming out from a LED, for instance, you have to just pick one at a time, just measuring what's happened to one photon at a time and how this photon can interact. So the idea is photon is good because it is immune to the gravitational forces, it is immune to the electromagnetical forces, it is immune to temperature. So the description, the physical description of photon is very easy, nice. So it's the point is that there is always something that is not nice. In this case, photon does not they do not like to interact with each other. So the point is how we can design a qubit that can simplify the interaction between this quantity, this photon. And and we have solved the problem looking inside the photon. Photon is a very complex system. It seems simple, but in reality, the mathematical description of a photon is very, very complicated. And you can store a lot of information inside one photon. And the idea is to have this multidimensional qubit. So qubit that are not just 0 and 1 in superposition, but in which you can superpose many, many states. And that's the trick about our qubit, that is a multidimensional qubit. And that's why we think that is much more scalable. The complexity of a circuit is simplified with our qubit approach. And it led us to enter in the edge quantum computer era, not just to design centralized big quantum computer, but decentralized small quantum computers that can be then connected in a sort of quantum internet.
Wow. That's pretty wild. I mean, because we've been talking about the stability, the room temperature issue and the stability of quantum computers, and that's why you hear the engineers at IBM and so forth talking about 100,000 qubit quantum computer as the aim, because that's when we will achieve stability. But what you're saying is, we have to approach this problem in a fundamentally different way.
Exactly. You have to start from a different approach, and you can solve the problem of stability in a different way. So is another approach. We have started not from the center, but for the edge, from the periphery, and starting from the edge, you have to think in a totally different way. And then if you use all the aspect of quantum mechanics, you figure out that you can solve the problem in a different way than to approach them from a classical point of view. It seems to me that a lot of people in the quantum field for quantum computation, they are still using the classical way to think. You have to enter in the quantum world totally and look at the quantum problem from a quantum point of view. And you figure out that you can use entanglement. That's why space is very nice to entangle qubit, and you can create a sort of, I say, rotosphere of nanosatellite that can be all quantum internet connected and all entangled. And they become a very big, powerful computer.
So you're talking about putting quantum computers in space, miniature quantum computer. This is blowing my mind.
Exactly. That's the idea, to design very small, very few qubit, very stable, and you conquer the massive parallelism because of entanglement. And so you have an entangled sphere of small computer. And in the space, the entanglement is much easier to achieve than in the Earth. That's why in the Earth, you have to put all in one place, because otherwise it's difficult to entangle all these things. But in the vacuum, in the space, it is much more easier. Of course, there are a lot of challenge. That is the dream.
You've got to get it up into space.
But at least it's possible. Fundamentally, from a physical point of view, it's possible. There are not all the challenge that you can have here in the Earth, and that's a really cool concept in the future.
Roberto, I'm glad that you mentioned advances in quantum algorithms, because they are, of course, a fundamental component to make a quantum computer whatever the architecture, usable. And it is important to highlight that quantum computers require different kinds of algorithms than what we have been using in our classical computers until now. Geordie Rose, who is the founder of D-Wave, another quantum computer company that announced their first computers now almost 20 years ago, and have since built based on low temperature so-called Josephson junctions,
Exactly. Yes.
cryonics-based computers with thousands of qubits. He uses to say that he would prefer running some problem on an Apple II, one of the first personal computers, with today's algorithms, rather than to run the same problem on today's supercomputer if he had to resort to the algorithms that were known at the time of Apple II. Meaning that if we are accustomed to the exponential improvement in hardware with Moore's law, software, the fundamental algorithms of software engineering have improved even faster. So the question to you, Roberto, your different approach, your photonics approach, implies that you have to also develop a completely new set of algorithms for your quantum network, or you can still take advantage of the existing libraries that are being developed for other quantum architectures.
Well, that's a great question. Yeah, the advantage of the quantum world, how the industry is developing in the quantum world is so different from the approach of the classic computation. In the classical world, and the classical computation in reality, what's happened is someone started from the hardware, and slowly in time, they build up all the other layer up to the software layer. Nowadays, in quantum, there is a parallel approach. There are people that are working on the software, people that are working on the algorithm, and people that are in some way working like us on the hardware side. So we want to use the only thing is to create a sort of quantum compiler, so a sort of link between the software layer that produce a quantum algorithm, and then we have just to design a compiler that take this algorithm and then it program our hardware. Every algorithm in quantum computation is an experiment. So you have to program the experiment on the hardware. So yeah, we don't want to recreate everything. We are not a full stack company. We just work on the hardware layer and on the minimum amount of software that can take the advantage of all the development that is done on the algorithmic layer. Algorithm is a big challenge because we need to invent a lot of new algorithms, but it's not the Rotonium work. We just stay on the hardware side, just to play with qubits.
Very interesting. Well, Roberto, just before we have a quick break, we like to get to know our guests a little bit more personally. So I've got a few quick questions that we like to ask for our guests. Short answers required, but that help us to know a little bit more about you. Okay.
Yeah.
This is the lightning round. So Roberto, what was the first science fiction or physics that you remember being exposed to as a child or in media, either via TV or books?
Well, I think that was some TV series about it was about Andromeda. Was a sort of of a movie about to discover the extraterrestrial life in the universe, and the other was about the moon. What's the name of the TV
Space
series?
1999.
Exactly.
And the Andromeda is probably Fred Hoyle's
Exactly, correct.
novel
Yeah.
that became also a movie
Yeah.
where
Andromeda
an
Strain.
interstellar cloud becomes
Glad to mention Fred Hoyle was one of the first my book that in terms of astrophysics that I have read in the past. So yes, Fred Hoyle. That's
Very
yeah.
cool.
You put me down back in 40 years from now. That's great. More than 40.
Okay,
Maybe
good.
50.
And what technology, this is a tough one. What technology do you think has most changed humanity?
Because I am in the computer space, I say computers, but maybe there are many other kind of things that can have changed humanity. But I think that computation, it's really something that I'm in this field. I like that.
Yeah.
I think that that's changed a lot of our life.
Okay, so name a physicist or an entrepreneur or a futurist that has influenced you.
Ray Kurzweil. It's
Good. Yeah, he's come up a few times.
but well, when I get involved with his first book about singularity, it changed completely my mind, and I have seen a lot of things that I have around me, but I was not able to put together. And
Awesome. And finally, is there a science fiction story or a future that is most representative of what you hope life will become?
well, let me say the most interesting movie to me is Matrix, the first Matrix, and just for understand how we can mix virtual reality and and the real reality, and how you can change completely the laws inside the virtual world, and we have to face these things in the future. So Matrix is the one that does not. It's a movie that you do not have any violation of at least from my observation of law of physics on the first, at least on the first Matrix. And it's a great inspiration, considering when it was
Yes,
developed.
absolutely. Well, Roberto, thank you. You're listening to The Futurists. We're going to take a quick break and we'll be right back with Roberto Siagri from Rotonium after these words from our sponsors.
Welcome back, everyone. This is the Futurists podcast. I am co-hosting with Brett King, and we have our guest, Roberto Siagri, who is the founder of Rotonium, a quantum computation startup that wants to put a network, a sphere of small, scalable quantum computers, all entangled in space.
In space.
Yeah,
let's just
right?
emphasize that, in space.
In space. So, Roberto, let's jump 20 years ahead. You have been successful. The constellation of Rotonium quantum computers is now complete. What will you do with it?
Well, I think that there are a lot of problems that humanity is facing that are not solvable with the traditional computers. And we know that, for instance, all the direction in the AI field, in the AI space, require a lot of energy. And someone is concerned about the energy that is required by this artificial intelligence algorithm. In this way, you can dramatically solve the problem of energy. You can have the computation that you require or you need to solve very complicated problem at a fraction of the energy that it is required now. So no more concern to put a threat on the Earth because of supercomputer. And ideally, there are a lot of problems that can be solved in terms of longevity for cure disease, for new pharma, new type of materials, all these things. So in reality, we want to solve the same problem that also other people are willing to solve, but in a more distributed and I'd say we want to democratize the quantum computation in order to benefit all. And I think that in this way, it's much more possible or more easy to be done than to perform all this computation on a central perspective directly in the Earth, inside the planet. So that's a matter of resilience. We want to be more resilient. We want to be more easy to access. You can access from any place in the Earth, from anyone at a fraction of cost. So that's the idea.
At the heart of your quantum computers, these devices you want to put into orbit, you talk about orbital angular momentum properties of photons, right? And this leads to greater stability, I'm guessing, versus the type of qubit structure in classical quantum computers like what IBM and D-Wave are building. But can you just explain why orbital angular momentum, and put it in layman terms, because we're not all physicists of your ilk, Roberto.
Yeah, it is just because we want to store more information. Normally, if you want to store more information in a single photon, the only way is to use orbital angular momentum. In reality, from a physical point of view, now I try to be simple. It's I do not know if I achieve on that. Orbital angular momentum, from the theoretical point of view, it can be seen as an infinite number of states inside a single photon. So you can store theoretically an infinite number of information in a single photon. Of course, this is not easy to perform practically, but you can at least have a multidimensional qubit in one photon. So we can overcome the problem of to have multi-qubit with multi-photons. So if you have, assuming that you are able to store 2 qubits in a single photon, they have to interact because they are part of the same system. There is no way. They have to be deterministic. So the two port gate, it is done. So this is a big problem, how you can design a gate with 2 qubits that is deterministic in photonics.
Right.
But if you use the same photon, because the 2 qubits are inside the same photon, it is deterministic. They have to interact.
That's even before we get into the whole entanglement issue between photons that you're talking about. How big are these quantum satellites going to be that you're putting up?
I tell you now, satellite is something that it will be in the future. Maybe we do not. We are not the one that will build that. We enable this network. Okay. I want to be down to stay with my foot on the earth. So we want to enable this new type of ideas. Right. So we are designing a very small quantum computer, not with a lot of qubits, with a minimum amount of qubit that is practicable, that can be practical to be used, and then someone can install this inside a nanosatellite. So we want to stay on the hardware side, so on the small, what they say, quantum processor, small quantum processor. That means at the same size of a silicon processor, not much bigger than. So we are talking about in the area of centimeter, of area, not square centimeter.
And Brett, it is worth maybe for our listeners to remark and to confirm that there is a kind of a format called a CubeSat, which is a 10 centimeter sided cube that is very convenient because you can pack them
Sure.
tightly in the useful mass that a rocket brings to orbit, and each of them can be relatively inexpensive. This standardization greatly improved the ability of rocket builders to sell a fraction of the available volume. So what Roberto is telling us is that we will see the Rotonium quantum processor integrated by someone else into the CubeSats and then delivered in orbit by probably the thousands, if not more.
Wow.
And Roberto is talking about some particular applications, but there are other people who are talking about putting relatively traditional data centers in space as well.
Of course. Yeah. No, I was
So
reading about that the other day.
we
Yeah.
are finally starting to feel that space is not an alien thing, but it is something that
Well,
we
because
can develop.
with Starship and so forth, the ability to launch at very cheap costs is now finally sort of coming into possibility. From $50,000 per kilogram to orbit. Back in the Apollo days to now, we're talking about potentially $100 per kilogram to orbit with Starship. It just changes the whole dynamic of what we can do with space.
Exactly. Yeah, and then we can enable quantum key distribution, we can enable quantum sensors. Whatever you are thinking in terms of quantum technology, you need a small computational unit close to the sensor, close to the transmission device. So in some way, we do not pretend to break the cryptographic code. We just want to enable this kind of things.
However, I have to ask you, Roberto, because a lot of people are very curious about it. Journalists love to write articles about the doomsday when all banking and all transactions
Q day, quantum day, yeah.
will be impossible because quantum computers will break traditional encryption. So, are you a good guy or are you a bad guy in this?
Well, we are not really interested now in that problem because it's a long-term shot. You need a lot of many qubits in order to do that. So we think that there are some practical use cases with few qubits, and now we are exploring them. Of course, going through this path, we can enable a much better quantum key distribution technology that can, in some way, prevent the break of the code, because you can enter in the post-quantum cryptography space. In some way, you can move private keys instead to use public and private keys. You can use private keys. So quantum key distribution is another direction, and it will be done from the space. It is difficult to implement quantum key distribution in the Earth because of all the problem that we have, but in the space it will much more easier to be implemented. So quantum key distribution, it's an area that is not our focus, but our small computer can help on this. And then quantum sensor, in order to be able to create a better way to explore the Earth and also the space. So you can, the breaking the code is, yes, it's one of the first things that create an excitement in quantum computation, because it was something that the classical computer cannot do. They need maybe 5,000 years. So quantum computer can do this job in matter of minutes of hours. So, and that's for sure, for all the government, it's a very interesting outcome. But for industrial sector, I think that there are many other problems that can be solved in the near term that can help humanity.
And just to make sure that those listeners among the ones that are following the Futurist podcast don't sleep well, the breaking of the quantum of the current encryption with quantum computers is not necessarily or not prominently about intervening in real-time transactions,
No, no, you are right.
injecting some
That's correct.
hacker at your bank.
You are
However,
absolutely.
if you have ever had a secret, and if you have ever protected that secret with current algorithms, and you have ever communicated that secret to someone else on a communication channel that is end-to-end encrypted, it is very likely, one, that someone actually stored that communication,
Yes.
and two, if it is worth it, in whatever number of years, they will go back and
Exactly.
see actually what was said. That is the point. And so it is really an interesting challenge. And if you have secrets, you'd better think about it.
Or better be on
So,
the cloud using quantum polymorphic encryption in the future, right?
for example, yes, because upgrading these encryption algorithms is an ongoing process that is going to protect privacy and enable free exchange of information for everyone. And Roberto, do you see Rotonium to be a constellation of quantum computing satellites only around Earth, or will we have Rotonium spheres surrounding Mars, or even a larger Rotonium sphere being part of the mega engineering project encompassing the sun itself? Is that how you
A
see
Dyson
it
sphere
Yeah,
progressing?
the Dyson sphere we are now
made out
there,
of
but
quantum
That's right.
computers.
yeah,
That's pretty cool.
and the Dyson was more related to the civilization in terms of how you are able to manage energy, and we are just in the beginning, so we need the Dyson sphere for the energy of the sun. Well, of course, this is a concept that can be also useful for all our space exploration because of the using the entanglement and using this kind of low power and radar computers. So space is for photonics because of the radiation and because of the distance. And implementing all the feature of quantum mechanics, it will be the right methodology to conquer the space at large. So in which way you want to implement it, it will just depends on how fast our civilization will evolve. But for sure, we need quantum. Quantum is our future. There is no other way. We cannot conquer the space without quantum. We cannot understand Earth in a better way without quantum. And we need also then the digital space. We need the inner space, inner in terms of quantum technology, inner in terms of digital augmented reality or digital virtual reality. And these two things combined together, it will give us a better understanding of the outer space. But if we do not conquer the inner space, we cannot conquer the outer space.
So Roberto, let's talk about why quantum is so often associated with huge advancements in understanding and science and so forth. So if we're looking at curing cancer, if we're looking at understanding dark matter, if we're looking at ways to advance our scientific understanding of the universe, as you're saying, why is quantum going to be able to do that better than classical computing?
Well, this is a question that Feynman have put on the table last century, in which he said, well, we do not have understand something because we are using now computers to do things that nature do very fast, and we need maybe months of computation. So the matter and the real world is computing not in the classical way. It's the rules of atoms are quantum. The rules of molecular are partially quantum. So if we want to understand, as I've said before, better the inner space. So something inside us or below us, we need to manage the quantum mechanics, and we have to compute using quantum mechanics. Otherwise, the complexity of the problem is so big that any classical computer cannot perform the job. So it's a matter of understanding how our reality works, and is a quantum reality. So that's why the quantum is the only way. At least this is, we do not have other theory now. We have the quantum theory. It works very well, as David has said. It's understand how our world is designed, is made, and we have to be able to make this computation on the atomic scale, on the molecular scale, if we want to design new material or if we want to create a new cure for our disease. So in reality, with quantum mechanics, we can rebootstrap life. We can rebootstrap everything. We can redesign all the processes, and like I say, we are the new gods. Yeah.
Mm.
Roberto, we started announcing, well, it is not announced here. I read press reports about your seed round. Congratulations. So it looks like that even though you are incorporated in Italy, you have embarked in the classical Silicon Valley trajectory of your startup being fueled by investor money and then scaling as it needs to not only research, but implement and produce large volumes of your devices. How do you see the future of your company? What happens from here as you go from R&D to implementation and then scaling?
Well, in all my career, I've always think in a global way. So in how to be able to be a sort of company that is not just in one place, but it's located in many places. It's a platform. I call the company platform company, in which you connect different research institute, different people from different places of the world. You have to figure out where are the people. The point is that in the past we have the so-called know-how. Now we are moving from know where and know who. And the point is to connect the who and in where they, whatever they are. So it's, I think that you can start in one place and then you can connect people in other places. And I like to think about, as you know, the Hollywood model. The movie companies does not have in the book the director, the actors, and all this. They are all part of a project. So you keep a core team in one place, and then you connect the best talent to achieve the result. So we start from here, but who knows where we can expand in the future. So it's just as you said, the seed. But this kind of seed are not like the real seed that the trees stay in just one place. Now the trees can expand in every place and connect the best talent.
So I wanted to sort of drill down on that, because we always like to finish on a positive note. And before we sort of wrap, let me just ask you then, describe for us the world in 20 or 30 years where quantum has changed the world. When we look back on that, what will we say this has happened because of our, the advancement of quantum computing specifically, do you think?
One thing is longevity, for instance, and the fast development of underdeveloped countries. So, and cure disease, or removing the problem of the environmental problem. Or we cannot afford this challenge if we do not have we are not able to dominate or to have a dominance in the quantum space.
That is a wonderful vision, Roberto. There are so many applications, and to see that quantum technologies will be able to benefit everyone on the planet is really the kind of positive note that we like to have on the podcast here. So if people are inspired by what they hear, how can they follow you or follow Rotonium? What is the best way to keep in touch with your development?
Well, they, now we have the social network, we have LinkedIn, we have many places where people can find us. So it is just a matter of the distance is one click. One click distance.
So they go and find Rotonium in
or
all
myself,
these
yes.
all
Exactly.
these. Are you hiring currently? Are you looking for talent?
We have just completed the hiring process for this year, and then we will start again next year. Yes, we have
Nice.
for the next year, and yes, and we have to grow fast also in terms of people, and that is a step-by-step approach. Because we do not have a lot of money, we have to think a lot more than spending the money. So well, but the process is that we have now closed the seed. We are now working for the round A, and with the round A, there will be the new hiring process that will start, and then we will have a round B, and of course, we are just in the beginning.
Awesome. Well, Roberto, it's wonderful to have you on the show. If people are sort of thinking about this thing and thinks it sounds a bit far-fetched to put quantum computers in space, by 2026, the International Energy Agency estimates that data centers around the world will be using 1,000 terawatt hours annually of electricity. How do you solve that? You
Exactly.
put data centers in space with solar, right?
Exactly.
So it is one of the available solutions to this problem. Roberto, it's wonderful to have you on. I every time I talk about quantum with someone who's in the field or a physicist, I come away thinking there's still so much I have to learn. So I'm sure we'll have you back on to talk about some of the progress. But thank you for joining us today.
Thank you. Thank you for the invitation.
And David, thank you for joining me in the hosting chair, as always.
Well, it was a lot of fun, and I hope to come back in this role as well.
Of course, absolutely. And that's it for this week, folks. You're listening to The Futurists. I'm your host, Brett King. We'll be back with another show. In the meantime, a shout out to the team at Provoke Media who help us put this together every week. So Sylvie Johnson on the social media side, Kevin Hersham and Lisbeth Severins on the production side. Thank you to the team for their work there. And as you know, we will be back next week with another episode. Until then, we'll see you in the future.